when an object is moving. Of course, in many practical situations, we need to know how fast, how slow, how faster, how slower it's happening. To do that, we need a physical quantity which describes the rate of change of the position. If we need a physical quantity which describes any important phenomenon, first of all, we have to give a definition, we have to name it, and we have to study its properties. This is a snapshot of an object at an instant t equals 1. It's moving. See? Here, now here, now here. Distance over time describes the rate of change of the position. Plus, this gives us a very important geometrical way to describe motion. We call it a motion diagram. A motion diagram shows the position of an object at different instances. And here in this picture, we can see it's been moving to the right. And if we call this, well, delta x, the time interval delta t, to characterize how fast it's moving, we would use this. That's what we call average velocity. If we wanted to calculate, well, if it's a one-dimensional motion, average velocity is fine. But if it's a two-dimensional motion, we know there is a difference between displacement and the distance. So there is another possible physical variable, distance over time. That's what we call the average speed. And if you look at these two equations, most commonly with the same variable, the same letter v. But this means average velocity, displacement over time. This means average speed, distance over time. So when you write a letter v, you have to remember what it represents in that particular equation. Now, in physics, we also have a much more convenient way to describe the motion, a graph as a position of a position as a function of time. Here what I have is a motion sensor. The motion sensor measures the position of an object over tiny time intervals, a fraction of a second. So the graph just basically shows you the position of this object at any instant you like. So what's going to happen if I start measuring the position? Why that line is horizontal? It's not moving. No matter when it's been measured, the position is the same. Velocity, of course, is 0. Now, I have to be quick. The graph clearly shows what was happening. So at every given instant, you can read the position of this card. And of course, you can see that, well, when position changes, the velocity is not 0. This graph calculates velocity, not speed. You will be using very similar setup in the lab very soon. I want to show you that motion is indeed relative. How would you know by looking at the graph what actually was happening? There is no way. If I had it covered by the screen, you wouldn't know if I was moving this card or if I was moving that card.